Well, hello, welcome again to Math 315, Analysis and Topology, and this is section 7. And in this section we're going to continue on looking at some theory about derivatives, and then we're going to look to the mean value theorem, very important theorem in mathematics and in analysis, and then we'll finish off with L'Hopital's rule. So as we saw before, we were dealing with continuous functions and also with limits. We had a sort of algebra of continuous functions and an algebra of limits, and we'd like to have an algebra of derivatives theorem, which then enables us to differentiate more complicated functions if we know the derivatives and the differentiability of simpler ones. So our theorem here says that if you've got two functions f and g defined on some real interval a, which are differentiable at some point c in that interval, then, if you take a linear combination of the f and g, that is, you multiply the function f by any real number you like, multiply the function g by any real number you like, and add them together, or subtract for that matter, of course, then the resulting function is differentiable at c, and you work out the derivatives in the usual way. And that's a fact you've been using all through school when you've been doing differential calculus. Also, the product of two differentiable functions is differentiable, and the derivative is given by the so-called product rule, where you differentiate the product of two functions, you copy the first, differentiate the second, plus copy the second, differentiate the first, and then you evaluate that at the point C. And finally, the quotient of two differentiable functions is also differentiable, provided you don't divide by 0 anywhere. So, and the derivative there is given by the quotient rule. So the derivative of f over g, now when I was at school I learnt it as, this is the top, this is the bottom. So you square the bottom, write it again, times the derivative of the top, minus the top, times the derivative of the bottom. Well, however you learn it, that's the quotient rule. It's worth seeing one of the proofs of these, so I'm just going to do the proof of the product rule, which is an important proof, in fact one that you would do with a good senior maths class when you're doing differential calculus. So again, we have to go back to the limit definition of what we mean by the derivative. So here I'm differentiating f times g. So our formula, or our limit definition, is we evaluate the function at c plus h, minus evaluate the function at c, divide by h. This is giving me the gradient of the secant, and then bend it around to make a tangent by taking h going to 0. So I've got f times g, so it's f of c plus h, g of c plus h, and then minus f of c, g of c, divided all by h. Now you can see from the product rule we're trying to get two separate terms out here, and so we do what we often do in maths, we subtract and add the same quantity. So I'm going to subtract f of c, g of c plus h, and I'm going to then add f of c, g of c plus h. So we subtract and add the same quantity, and I can then split this limit up into two limits, this one here, and then I can split it up into this one here. Break up the fraction into two fractions here, and in the first one I've got a common factor of g of c plus h, so I can factor that out, and I'm just left with f of c plus h minus f of c, all divided by h. And the second one I've got a common factor of f of c, so I can factor that out, and we're left with g of c plus h minus g of c all over h. Now as h goes to 0, then this h here goes to 0, this just becomes g of c, and here we get the derivative. This is just the limit of the derivative, or the derivative formula using the limit, and that's just f dashed of c. And similarly here, f of c we copy down, and this is the derivative of g. And there we have the product rule. So just as a simple example of that one, we've got the function f of x is e to the 2x times sine 3x. This is the product of two differentiable functions, and so is differentiable. And indeed we can work out the derivative in the usual way, just using the product rule. Just quickly zip through this here. By the way, it's a good practice to put brackets around your sign of around the 3x here. You could put it around here as well, but there's always the danger here that you might cancel or do something silly with this. It's sine of 3x, and so we should put little brackets around us to remind us not to do anything silly. So to use the product rule, you copy the first, differentiate the second. So sine differentiates to cos, and then the chain rule says we're going to multiply by the derivative of the inside, the 3x, which is 3. So first by derivative of the second plus the second function, which is sine 3x, times the derivative of the first. Now e to the 2x differentiates exactly to itself, and then the chain rule says you've got to multiply by the derivative of what's upstairs, which is 2. And then finally all I've done here is I've just factored out an e to the 2x just to tidy it up a little bit. So there's an example of the product rule. Now we define higher order derivatives, of course, are defined inductively. So to get the nth derivative, you just take the n minus 1th derivative and differentiate once more. So the second derivative is just the derivative of the first derivative. So as a simple example, we're going to find the 10th derivative of sine of 2x, just as an example there. So here's sine of 2x. F of x is sine of 2x. Again, good idea to put little brackets around your 2x so these symbols don't go floating off somewhere else. And I'm going to do this twice. When you differentiate sine, it goes to cos, and when you differentiate cos, it differentiates to minus sine. So the sine 2x differentiates to minus sine 2x when you take the second derivative. And the chain rule says, well, you've got to take a 2 out the first time and another 2 out the second time, so you get a 4 here. You can put the intermediary step in if you like, just to double check. So that's what happens when I do it twice. So if I do it twice more, then if sine goes to minus sine after 2 derivatives, then minus sine is going to go to minus minus sine, i.e. plus sine 2x after the 4th derivative. So it basically goes sine cos minus cos and then back to sine again. But again, if I do 2 more derivatives on this, I've got to pull 2 out twice more, so I'm going to get 4 2s are 8 2s are 16. By the way, we generally, for derivatives beyond 3, one often uses Roman numerals to show the derivatives here. So you can also just put numbers here. You can put round brackets 4 or round brackets 8 and so on, but traditionally one uses Roman numerals in this context. So that's the 4th derivative. I can jump now to the 8th derivative, and sine of 2x is still going to stay as sine 2x after I do another 4 times, except I'm going to pick up another 2. I'm going to pick up another 2 4 times, so another 16, and 16 squared is 256. So that's the 8th derivative. And finally, I do it twice more to get to the 10th. So sine goes to cos goes to minus sine. I pick up another 2, that's 512, and another 2 is 1024. So there's the 10th derivative of the function sine x. Now, we come now to this concept of continuously differentiable functions. And we're going to consider this function here. You might like to get, if you've got a graphics calculator or something, you might like to draw this one. It's x squared sine 1 on x if x is not 0. You can't put x as 0 in here, but it takes the value 0 when x is 0. We've had a look at this one before, and we'll show in a moment that we'll mention again that this function is in fact continuous, and it has a derivative. And the derivative, if x is not 0, the derivative is just obtained by differentiating this thing. Now I've got to use the product rule here. So to get to the product rule, well, I'll do the second bit first. So copy the second function, that's sine 1 on x, and multiply by the derivative of the first, that's 2x. And then I'm going to have, I've done it over the side here, I'm going to have x squared, and I've got to differentiate sine 1 on x. So sine goes to cos 1 on x. Then I've got to multiply by the derivative of the inside, the 1 on x. So 1 on x is x to the minus 1. Differentiate is minus x to the minus 2, which is minus 1 on x squared. So with a chain rule, I've got to multiply all this by minus 1 on x squared, and when this all cancels and simplifies, you should check that you get minus cos 1 on x. So if x is not 0, then the function's continuous, and its derivative is given just by this. Now again, we have to just check it's continuous at 0, so we've done this before, but at x is 0, we can use the pinching theorem. I'll leave you to check the details, and you can prove that this limit exists and equals 0, and that's the value at 0, so that means f is continuous. Okay, so this funny looking function here is continuous at x is 0. Moreover, is it differentiable at x is 0? Well, then again, we have to go back to the limit definition. So if x is not 0 for the moment, we're going to use that first definition of the derivative, the limit. So we've got f of x minus f of 0 on x minus 0. And we're going to then take a limit as x goes to 0 of this. So you plug this in, you get x squared sine 1 on x divided by x is just x sine 1 on x. And again, we can use the pinching theorem. Gives us that this expression here also has a limit of 0 as x goes to 0. And that says that the function f is differentiable at x is 0. And that means it's differentiable everywhere. Okay, so let's just put that together then. This funny looking function here is continuous at 0. It's differentiable at 0. And in fact, the derivative is 0 at 0. However, when you look at the derivative itself, if x is not 0, that's what the derivative looks like. And if you try and take a limit of this beast as x goes to 0, well, that limit will exist here, but this one doesn't. You can't take a limit of this as x goes to 0. You get cos of 1 on 0, whatever that means. So, what's that? That is telling us then that although the derivative exists, the function is differentiable at 0, the derivative itself is not continuous at x is 0. Because when you try and take a limit of the derivative, this limit doesn't exist because of this cosine term. Now, you need to get your head around that. So we've got a function here which is continuous, it's differentiable, but the derivative is not continuous. And so we can make a distinction between a function being differentiable and having a continuous derivative. So that leads us to introduce a definition. So if f is a function, defined on an open interval a, we say that f is continuously differentiable on a if the derivative exists and is continuous. So if the derivative exists and is continuous, then we say the function is continuously differentiable. More generally, if the function is k times continuously differentiable, that is, you can take the derivative k times and each of those derivatives is continuous, that means then we're going to say in that case that f belongs to ck. We read this as ck. This is a ck function. So f belongs to ck means that you can take the function f has derivatives up to order k, and each of those derivatives is continuous. If a function's continuous has continuous derivatives of all orders, no matter how far you go, then we say that f belongs to C infinity, or f is a C infinity function. That simply means you can differentiate it as often as you like, and the derivative always exists and is continuous. Now, happily, most of our favourite functions, like sine x and e to the x and x to the n, where n is a positive integer, etc., these are all C infinity functions. You can differentiate them as often as you like, and every derivative is continuous. Now there are many functions which are not C infinity functions, and I'm going to do a couple of examples of this one. So we're going to consider the function f of x is equal to x squared if x is positive, 0 if x is negative. And we're asked to show that f is a C1 function. That means it has a first derivative which is continuous, but not a C2 function. That is, the second derivative exists, but it's not continuous. Now, here's the working out for that example. So here's our function, and it's nice to draw a little picture of this. So it looks like x squared if x is positive, and it looks like just 0 if x is negative. So it's coming in here and going up like that. And even in this rough sketch, it looks as though it's going to be continuous. It looks as though it's going to be sort of smooth a bit here as well, except we'll see that the second derivative is not continuous. So there's a change of concavity, in fact. So f is continuous at x is 0, since, just to put all the gory detail in, if you take a limit as x goes to 0 from above, from this way, of f of x, then you're getting 0. If you take a limit, if you take x go to 0 from below, well, you're also getting 0, and that's the value of the function. If you whack x to 0, you get 0. So that tells me the function is continuous. If you then differentiate each piece of the function, so you differentiate the x squared, you get 2x, you differentiate 0, you get 0. This function also is continuous. The derivative is continuous, since if you take a limit as x goes to 0 from above, that's this bit, as x goes to 0, this goes to 0, and this is already 0, and the derivative at 0 is 0. You put x as 0 in here, you get 0. So that means the first derivative is continuous, and so we conclude then that f is a C1 function. If you now go to the second derivative, you differentiate 2x, you get 2, and 0 just stays as 0. And clearly this function is not continuous, because if you go to take a limit as x goes to 0 from below, then you're looking at this one, and that's 0. But f double dashed of 0 is 2, and these aren't the same as each other. So the second derivative exists, but it's not continuous, so this is not a C2 function. Second example was to show that this function, we've got sine x if x is bigger or equal to 0, and x if x is less than 0. We're asked to show this is a C2 function, but not a C3 function. So again, here's the setting out of this. We can be a little bit slightly shorter in the setting out. So there's the function. Nice to get a picture. So it looks like sine x if x is bigger or equal to 0. And it looks like y equals x, which is just coming up here. And again, it looks like it's going to be coming and be continuous. It looks fairly, even in my rough picture, it looks fairly smooth. And we're going to see that the concavities match, but when we get to the third derivative, it's no longer, we no longer have a continuous function. There's a special name for the third derivative. It's called, I think it's called the jolt of a function, but it's not used a great deal, but anyway. So firstly, f is continuous. So I'm not going to go through all that again. You can see that if you take a limit of sine x as x goes to 0, you get 0. You take a limit as x goes to 0, you get 0. So that's going to be continuous. If you differentiate both of these, sine goes to cos, x goes to 1. And again, the limit, as you go to take cos x and take a limit as you go towards 0, you get 1. And then if you go from the other side, you also get 1. So I'm just going to say the limit as x goes to 0 of this thing is 1, and that's equal to the cos of 0, which is 1. So that's telling me at the moment f is a C1 function. If you differentiate again, well, cos goes to minus sine, and 1 goes to 0 when you take the derivative. I should put an x in here. And again, if you take a limit as x goes to 0 from this side, sine of 0 is 0, and this side the function is 0, and the value of the function is 0. So that tells me the so that means that f double dashed is continuous. So at this stage, this tells me it's a C2 function. So therefore f is a C2 function. It's got a continuous second derivative, but if you plough on and get the third derivative, you differentiate minus sign, you get minus cos, and naught differentiates still to naught. Now, if you take the limit as x goes to 0 from above, well, the cos of naught's 1, so this becomes minus 1. So as you take a limit as x goes to naught from above, the third derivative goes to minus 1. And that's not equal to the limit from below, which is just 0. So that means this derivative exists, but it's not continuous. So we say that f is a C2 function, but not a C3 function. And that's the end of this video.